very, very crucial that we understand our batteries better, and why understanding batteries is key to the energy transition to an electrified future. So how can batteries help our energy transition? So as we all know, COP26 happened. The government set 2030 targets, which were quite ambitious, and hopefully we can reach them. And with batteries, should be the way. But with net zero for 2050, these targets are ever approaching. And as previously talked about, regarding CCUS, we have a lot to do to get to those targets. It's very important that we kind of understand the importance of this, because this is all of your futures. It's very, very important. So as we try to hit these targets, we're becoming more and more electrified. So the electrification is changing things that are reliant on fossil fuels, like our electricity, like our cars. Things that, that we can reduce and use is by doing electrification. So the other thing that is helping our electrification is renewable energy, and renewable energy can help or works with using battery technology. So, I mean, we get solar, we get hydro, and that feeds into battery power, and that feeds back into our grid, which I will talk about a bit later. So a brief history about batteries and how they work. So the first battery was made by Alessandro Volta. It was the first one to create stable current, and how he made that was he had piles of, well, if you can see there, the voltaic pile by Alessandro Volta, and that was copper and zinc on piles piled up together and separated by some brine, either on cloth or on cardboard, to conduct electricity. And that was actually invented in the 1800s. So we've actually had batteries for a very, very long time. The most basic battery is the Lennon battery. Anyone can make this if you want to do it at home. You just need a copper nail, copper coin, and a galvanized nail, and a couple of wires, and a little LED. And how that works is that there's an electron transfer between the copper and the galvanized nail. And that electron exchange is what causes the bulb to light up. And so I guess you can see here what our typical battery looks like as a cross-section. You also have a little bit of a schematic here of what's inside our batteries that we get. So these are a couple of common batteries that we use every day. The Alpine batteries, well, everyone gets. That's probably inside this remote that I'm using right now. And the Alpine battery was invented, and the first commercial and public supply of batteries that anyone could use. The chemistry is zinc and magnesium oxide, and the benefit of it was that it was able to provide a stable electricity throughout its full duration. It's non-rechargeable, but the issue with Alpine batteries is that they're very hard to recycle. We just have to dispose of them. There's nothing we can do about it. The next most popular one is the nickel metal hydride batteries, and that's done with nickel compounds, nickel elements inside the batteries. And what the benefit of those was that it was rechargeable. And that was actually done by the automotive industry. Volkswagen and Daimler-Benz were the ones that helped that development. And they wanted something that could sustain a charge. So you can get about 500 cycles. A cycle is a charge up and a discharge of a battery. So you can get about 500 out of a metal hydride battery, but every cycle you get a loss of performance. So you get a bit of degradation every time. The reason that you can recharge these batteries is because it's got nickel inside, and so when you use an alkaline battery and it's a one-way cycle discharge, eventually that will run out and the chemistries will stick to those plates that I showed in the earlier slide. In this case, you can put electricity into the battery and the reverse can happen and it can recharge those plates, if that makes sense. So you have the anode and the cathode in this previous slide, and those oxidation and reduction events can reoccur. And then lithium ion batteries. Lithium ion batteries were the revolution, realistically. In the 1970s, the Japanese did a lot of research into lithium ion and lithium ion implementation. Sony was the one to commercialize it in 1991, and now we've got lithium batteries in everything. Everything we use, from e-bikes, e-scooters, our phones, even our cars are now using lithium ion batteries. And they've really taken over the market. And the benefit of a lithium ion battery is that you can get double the amount of rechargeability than a nickel metal hydride battery, but as well, the degradation is very, very slow. So unlike nickel metal hydride, where every time you use it and discharge it, it degrades, the degradation was a lot slower in the lithium ion battery. So now I'm going to show you why we really need to change our understanding of batteries. And I'm going to show a couple of videos that show what happens when we get thermal runaway. And thermal runaway is very, very detrimental to our push towards electrification. What's happening here is that it happened in France about 3 weeks ago. So a bus was travelling along, and all of a sudden got a lot of emergency signals, everyone evacuated, and essentially this bus, as you can see the picture on the left of it smoking, and then the picture of the right of it exploding, pretty much. That was due to thermal runaway. So there was not, every battery, a lithium battery, has a thing called a battery management system in it. And a battery management system allows, is designed by the manufacturer to tell, say when the battery is charging and discharging. And so a lack of understanding of that is something that can cause thermal runaway. And then in the next video, if I can show it, was actually e-scooter blowing up inside a HABS. So it's quite comical because the guy's not really dressed and running around trying to put out a fire, but it's extremely dangerous and extremely scary. There's a lot of fires and household fires that have occurred because of this, and it is very detrimental as we move towards electrification. So this happened in South Australia about 3 years ago. This was, they had built a big Tesla battery site in the countryside, and what happened was, there was mismanagement of the battery system, and some batteries set alight. The real big issue with battery fires is that they're impossible to extinguish with conventional methods. So you have to get a specialist team and a specialist equipment to be able to put out a battery fire, and that went on for 3 days, as you can see by the title. So I'm going to talk about a little bit of research and a bit of a couple of changes that we need to make in our understanding so that we can utilize batteries a bit better. So we can see the equivalent circuit model. So that's what's used in all battery management systems. So all BMS is used an equivalent circuit model. It's very low compute, very easy to model, but it is empirical. So it uses a lot of assumptions when making. It works well, but it's not the best way to understand it. The next way the other way to understand it is using physics-based models. And physics-based models allow you to understand the internal state of the battery, which is quite crucial. And that allows us to do things like work out nonlinear aging of the battery, things like how to optimize the fast charging because of lithium plating and understanding lithium plating. There's a couple of applications there where understanding those will allow us to be able to implement batteries better. The other thing that, especially about energy, that what they specialize in is thermal modeling and the distribution through 3D. And so being able to look at the 3D model and how the temperature flows through the battery is crucial to stopping thermal runaway. So I'm going to show a couple of slides from the Electrochemical Science and Engineering Research Group from Imperial College. And this is talking about degradation. I think degradation is probably the most critical thing that we need to understand and work out about batteries. Degradation is the thing that can stop thermal runaway, and is the thing that can allow us to predict the end of life of a battery a lot more accurately. So as you can see, the green squares show the primary factors that can affect a battery. And then on the next slide, you can see how these are done in a flowchart. So if these first 5 green things occur, then following on, there's almost like a domino effect. And so it's understanding these 5 main factors, which are particle fracture, lithium plating, solid electrolyte interface growth, the PD structural decomposition, and the particle fracturing. So understanding that is our pathway towards understanding degradation a lot better. We can't physically see degradation. The ways that we kind of know that a battery is degrading is there's power fade and capacity fade. And power fade is just like you're not getting as much power out of the battery as a fade. And the capacity is definitely changing when you first start using it. And seeing those happen is a very big sign that your battery is degrading quite significantly. Here's a further, a bit more elaborate flowchart, and it shows how different instances of things happening will affect, as it will have a flow-on effect to the next set. So it goes from green to red to purple to pink. And pink is what we don't want, that's thermal runaway. We don't want that. So the best case of application is through grid storage. So when we're applying degradation to grid storage, we can kind of understand the best it the best way. Realistically, we've got all these popping up on the English countryside now. Grid storage using renewable energy to supplement the grid. And how it works is that our national grid will sell contracts when they really need supply. So when you wake up in the morning, turn on your kettle, and when you go home at night and have dinner, this is when you're going to be using your power the most. And at those times, sometimes the grid can't cope with those surges in demand. And so they sell contracts to grid storage companies like Gresham House, Field Energy, Eel Power. These companies, EDF, all these companies will trade electricity on the grid. And so when they're going to trade this electricity, they have to take into account degradation, because they need to understand that they have to use their battery in their cycle life and not too much, and not cause thermal runaway, like we saw in the Australian example. So there's a couple of ways, and there's a little chart here to show and get an example of the trends of supply and demand throughout the day. And how do these companies make a profit? Well, they sell the contract. Well, they buy the contracts and they sell it at a higher price. So they buy when it's discharging. They buy when they're charging. They buy a contract when the demand is low, and then they can do things like day ahead, intraday, and frequency trading, which means that they will predict using algorithms and stochastic optimization to kind of predict what the supply might be a day ahead. They can also do what the demand might be in the day. So if you're looking at the supply within the day, they'll be trading at a higher frequency as well. So they'll be doing a lot of trades within the day. So to conclude, batteries are very key to our electrification. We need it to hit our targets. Testing modelling of batteries is essential for our informed application going forward in the future. Understanding battery degradation is critical to our green future. So, if we have more and more instances with lithium-ion batteries, government's going to turn around and be like, look, we can't use these anymore. People's safety so understanding degradation actually allows us to optimize our usage of batteries a lot better. And grid supplementation to renewable energy will really help us hit our COP26 goals. Thank you for listening to my TED Talk.